In this video, I'm going to be going over Huffman Code Compression and how it can be used to compress any type of data by converting it to a bit stream that can then be decoded later. So first I'm going to start off with an example of what a Huffman tree is and how it can be used to compress data. So a Huffman tree will work by using zeros and ones to convert a letter to a bit representation. And so if we go left, it'll be a 0, and if we go right, it will be a 1. And once we reach a leaf node, we can then associate it with a letter that is associated with it. So for this example, I'm going to be using the text string. This is the string I will be encoding as the text that will be used for this example and how it's going to be used. So first I'll start off by creating a profile of the text so that each letter inside of it will have a frequency of how often it occurs. So we'll start off by creating that profile dictionary and then go through each one of them and then either increment it or initialize it as 1. And then once we have done that for every letter, we'll then return that profile so that we have it for this set of strings. So when we do that, this should be the frequency table and the letter associated with each one that we're going to get for this example. So once we have the profile, we can then build the Huffman tree that we're going to be using for this example. So we're going to first start off by creating a priority queue, and then we're going to go through each letter in the profile, which will be the key value in the dictionary. And then we're going to create a node for each letter and then add it to that queue. And so when we'll do that, we'll create that node, and then each one of those nodes will have a letter and a count associated with it. The count will be the profile, will be the frequency from the profile. We'll then insert that new node into the priority queue, and then once we have each one of those inside of the queue, we can then build the tree. And we'll do this by combining the two lowest count nodes until there is only one node left inside of it. And so we'll start off by dequeuing two nodes X and Y, and then we'll create a new node Z, and then we'll use the Z count as the combined count of X and Y, and then we'll use the Z.left and Z.right respectively as the X and Y nodes, and then we'll reinsert the Z node back into the priority queue. And we'll do this for each one until we have only one node left inside of it, which will then be the root node of the entire Huffman tree, which we will then return, and which then we can use to create the Huffman tree. So this is an example of what the Huffman tree could look like for this example that we're going to be using. Each time we go left or right, we'll add a 0 or a 1. And then once we get all the way down to the leaf nodes, we'll then have each letter associated with it put into the queue. And then we'll use the codes for each one when we encode the message. So now that we have the Huffman tree, we can create the encoding map that we're going to be using for this example. So we'll start off by creating a map, which will be a dictionary of letters to binary strings. And then we will traverse the tree and build the map that we need to be able to use this. So we first check if the node is a leaf, and if it is a leaf, then we'll add it to the map so that the code associated with it is then used. Otherwise, we'll go either left or right and then append to the path either a 0 or a 1. And once we have done this for each letter in the Huffman tree, we'll then return that map, which will then have the encoding values for each letter. So this is an example of the encoding map that will be returned from this function, with each letter having an encoding associated with it that can then be used for when we encode with the function. So now that we have the encoding map, we can then encode the text, and we'll pass in the original text and then also the encoding map that we're going to be using for this. And so we're going to go through each letter in the text, and then we're going to look up the encoded value within that encoding map that we just created. And then that's going to return the result for each one, and then return the final value, which will be a bit stream of text. And so this will be the encoded string that will be returned. Then this is the bit representation of the text that we had earlier. And now we'll go over how to use decode, which will take in the encoded string text which we just had, and then it will also take in the Huffman tree in order to find each letter associated with that value. And so we'll traverse this tree in order to find each leaf node, and then once we find a leaf node, we'll then append the letter back onto the result. And then once we have gone through and found each leaf node, we'll then return that result, which will then be the decoded string that we had originally. But in order to fully have compressed and string, we first need to convert it to a bit stream. So if we're going to send this over a network or anything, we're going to need to convert from the encoded string into an actual bit stream that we can use. And so we can do this by creating a byte array, and this is done by going through the encoded string that we created earlier, and each byte is 8 bits, so we go and we find 8 bits and then basically convert each one of those 8 bits to a byte, and then we'll just use that as a result. And then once we have the byte array, we'll then return that result so that we have the entire byte array that we can use to send that data over a network or anything that we need to. And then we're also going to need to convert from the bit stream in order to use that in our code that we have. So we'll first build a string by converting the bytes back into the bits that we need to be using. And so we'll take that, and then once we have all those bytes and we convert them back to bits, we can then use it with the decode function in order to use it and find the decoded string. And so now we're going to go over a test and make sure that this code will actually work so that we can use it correctly. So we will now be going to the test function where we'll be testing out the functionality that we just went over. So for this, I'll be using the text string that we used in the example, and then we'll then create the Huffman profile, and then we'll also create the tree and the encoding map, and then we will encode the data and then convert it to a bit stream. And then we'll want to check to make sure that there is the byte array that is equal to this value, so that we can know that it was converted correctly to a bit stream. And then we'll also compare the encoded value to make sure that it is the correct encoding that we expect it to create. And then we'll also create the encoded string from the bit stream that we created, and then make sure that it's also equal to the encoded value. And then we'll also get the decoded text by calling the decode function and making sure that it is equal to the original string that we have. So now I'll run these tests to make sure that everything is running correctly. We'll look at the test results, and it looks like everything was run correctly, and that the encode, decode, and the tree is all built correctly. So now we can go over the performance of the encode and decode functions. So the encode function should be O of n performance, where it goes through each letter in the text, and then we'll find the encoded map value and then return that. And then when we use decode, it would be O of n if the Huffman tree is balanced, but it could go to O of n log n if the Huffman tree is unbalanced and not efficiently storing those codes.